All right, guys, we're back at it. As I said on Friday's meet, for those of you that are continuing in the math field, finishing up the curriculum for you guys would be pretty important. For those of you that are not considering going into the math field, you're going to be doing option 2 for homework. So you don't, if you elect not to do the rest of the curriculum, that is fine, but you have to continue with the optional homework. Okay, so we left off at area between curves, and that was around 320. If you go on my Google Classroom and you're looking at videos, that was the last piece where I stopped. I switched gears into differential equations because that's when AP decided that they were going to leave this whole unit out. So before I can get into volumes of revolution and into AP questions that apply this concept, I need to go back and review the area between curves. So the worksheet that you have is what I gave as a quiz last year, so I figured that would be a good worksheet to just reference and to get back on track. So area between curves, you should have this in your notes somewhere, but just if you don't, you lost it, enter just refresh. Let's go through it. It's when you have, when you're given two functions, the first thing you want to do, if possible, sketch the givens. Then you're going to have a visual, and you're going to either have something that might look like this or something that might look like this. Your second objective is to decide which rectangle you're going to draw to find the area between the curves. So there's two options. You're either going to draw a vertical rectangle. So if you see, I made a vertical rectangle here, and how do you know if you're using the correct rectangle? The top of that rectangle and the bottom of that rectangle should always be touching the same function from the beginning. So I have a horizontal function and I have a quadratic function here. And so as I move from left to right, that top of that function stays along that horizontal the constant function, and the bottom of that function stays along the quadratic. So I know for this scenario, a vertical rectangle would be appropriate. If that's the case, you need to make sure your equations are in terms of x. So that means that you would have something that says y equals x squared minus 2x plus 1, and y equals, let's say, 5. Okay, so everything should be in terms of x. And that's when you go ahead and you find your bounds, which we'll talk about next, and set up your integrand, top function minus bottom function. And your variable of integration is going to be dx, and that's 100% because of the vertical rectangle. If your drawing looks something like this picture here, where the area between curves looks like so, if I tried to do a vertical rectangle, that would not work. I'd be touching the same exact curve. So I'm forced in this problem to do a horizontal rectangle. And if you see, the right side of that rectangle is hitting this vertical line, and the left side of that rectangle is hitting this quadratic. Whether I slide it from the top to the bottom, that's the right side is always with the vertical line, and the left side is always with the quadratic. So if that's the case, you would be setting up a horizontal rectangle, and instead of doing top function minus left function, it's going to be the right function minus the left function, and your variable of integration will be dy. If it's going to be if it's going to be a variable of integration in dy, all your equations must be in terms of y. So that means you'll have something that looks like x equals y squared plus 2y and x equals 6. Okay, moving on. After you've decided which rectangle you're going to use, you're going to find the bounds. Now the bounds are either given to me, so I'll look at it and say, okay, I'm not going to use that for a function. I'm going to use it as a bound. And how would I know? If you have your variable of integration in terms of x, it's dx, well, my bounds are going to be x values. If it's dy, my bounds will be y values. It's coming off the y-axis. Here, those bounds are coming off the x-axis, and those bounds are occurring where those two functions intersect. So if they don't give you bounds, you can go ahead and set the equations equal to each other to find the bounds. And the last piece would be to set up the integral. So this was just all review. So let's give number 1 a try together. So if I look at this, my first step was to sketch the givens. I know I have a quadratic and I know this is linear. So I'm guessing, now you might not know exactly what this parabola looks like. So I'm guessing it could look something like this, and it could have something linear like so, but I'm not sure. Let's figure it out by finding the bounds. Here, because everything is in terms of x, I'm assuming this vertical rectangle will probably be safe to use. And it will come true as soon as we go through and find the bounds. So now to find the bounds, you're looking for the point of intersection. So you're taking x squared plus 2x plus 1. Whoops. Let me rewrite this in ink. X squared plus 2x plus 1 and setting it equal to x plus 1. And you go ahead anytime you're solving for x with a degree higher than 1, you set it equal to 0. So I minus that x over, minus that 1, and I get x squared plus x equals 0. And then you GCF x plus 1, you get x equals 0, x equals -1. So it seems that the points of intersection are happening, and we would say that this would be, so my drawing's a little off. We're going to say at x equals 0 is the point of intersection, and at x equals 1, -1. Okay, so I know those are my bounds. 0 is the higher one, -1 is the lower. All right, I've already decided that this is going to be a vertical rectangle because all the equations were written in terms of x. So I know I will have a dx. So now I'm trying to decide which one's the top function and which one's the bottom function. And I know this will be dx. Now, again, you might have no idea what this function looks like. So you might not know which one's on top. Is it the linear? Is it the quadratic? So the trick that we picked, we said that you could pick any number in between the bounds, and plug it into each function and see which one gives you the greater value. The greater value will be the top function. So if I pick -1/2 and I go ahead and put -1/2 plus 1, well, that's going to be +1/2. So g of x would give me +1/2 if I went ahead and tried to plug that in. If I took -1/2 and squared it, that would then become -1/4. And then if I went and took -1/2 and times it by 2, that would just be -1 plus 1. So I'd get -1/4 as my value. Well, +1/2 is definitely bigger than -1/4. So this tells me and confirms that x plus 1 is my top function. So I did end up drawing this correctly. That's my top function, and my bottom function is the x squared plus 2x plus 1. So now that I have this up, you just want to go ahead and clean up the integrand. And so you're just going to do that by distributing that negative. And when I go ahead and do that, 0, -1, I end up getting -x squared. This gives me a -x, and the 1's cancel dx. So now that you're here, you just set up your integrand ready to go ahead and find the area between the two curves. Not that this is relevant for this year, but in the past, a lot of times the AP would say just set up the integral, no need to solve. So always pay attention if you have anything like that in your future courses. So now the biggest mistake is kids forget to integrate. So we go ahead and do that. We're going to add one whole to an exponent, divide by that new exponent, and x squared over 2. And now you're just going to go ahead and do the FTC. And I know that you haven't really been practicing too much without the calculator, so we're back at that. So this is going to be -0 cubed over 3 minus 0 squared over 2. And when I have zeros all around, that's 0 minus, and this is going to be a negative. And this is where you want to be very careful. Even me, when I'm doing this, easy to make mistakes. Okay, make sure you are careful with those negatives. -1 cubed is negative times a negative is a positive 1/3. And then here you got negative 1 squared is positive, so you get minus 1/2. And here, if you do not have the use of a calculator, this is you're going to require to have a common denominator of 6. So you're going to have 2 6 minus, this is going to be 3 being multiplied, 3 6. So you're going to get a negative 1/6 times a negative, and you end up getting 1/6 is the area between the curve. Okay, to the second problem. When we're looking at this, I want to try to sketch the diagram, the gibbons. And so when I do that, I see I have a sideways parabola shifted to the right too. So I know it's opening to the right because that y squared is positive. So it looks something like this. X equals 0 is just the y-axis. So I know that's this function, this y-axis right here. That's going to be my x equals 0. And then they tell me to find the area between the curves y equals negative 1. Y equals negative 1 is right here. And here y equals 2 is right here. So the section that I'm trying to find, the area between that's created between those bounds, is this highlighted section. So when I'm looking at this, I'm saying, oh, this is definitely not going to be a vertical rectangle, because if I do that, I'm not even getting this curve involved. This is going to require a horizontal rectangle. So I know that my integrand is going to be with right minus left, and in terms of dy. So therefore my bounds have to be y values. So what two y values were given to me are right here. Those are acting as my bounds. So it's going to be 2 and negative 1. And then I need to pick right versus left. Well, here the right is the quadratic, y squared plus 2. And the left is this x equals 0. Now say you weren't sure, you could just plug in 0 because that's a value in between negative 1 and 2. If I plug in 0 here, I'm going to get 2. If I plug in 0 here, well, there's nothing to plug in. There's no y that I could plug into, so it's still 0. The 2 is bigger, that's why that one comes first. So now when I'm here, this is the correct setup. I'm going to clean it up. It's 2 negative 1 y squared plus 2 dy, and now I'm ready to integrate. And so when I integrate, it just becomes y to the third over 3 plus 2y, and we're going to do the FTC upper bound. So it's going to be 2 cubed over 3 plus 2 times 2 minus negative 1 cubed over 3 plus 2 times negative 1. And so when I clean that up, I get 8 thirds plus 4 minus, and this is going to be a negative 1 cubed is negative 1/3 minus 2. So cleaning up those parentheses, you need a common denominator. So I'm going to multiply this by 3, and so I'm going to get 8 plus 12, so I get 20 over 3 minus, I need a common denominator here of 3, so I'm going to get a negative 1/3 minus 6, so I'm going to get negative 7 over, that's negative 6, 3, then negative 7 over 3, and so a negative negative is a positive, so that's going to give me 27 over 3, which gives me 9, and that would be the area between those curves.